So today we're going to be starting lecture, just one second. Okay, lecture 3, and we're going to be talking about measurements and observables. By the way, the lectures and the lectures are posted on my website, and the videos are on YouTube. So you should be able to find all the recordings as well as the notes. All right. So reviewing lecture 2, we discussed how in lecture 1 we started with the these two experiments, and then we said we started modeling it using a complex vector space that we call the Hilbert space. It's a d-dimensional complex vector space. So d equal 2 dimensions. For example, you could think of it as a basis for it. You could think of it as 1 and 0 that we denoted by plus ket. We call these column vectors kets, and or 0, 1, which is we called it ket minus, right? So these are column vectors. In general, a general column vector, which is like complex, where we denote this, for example, with ket alpha. Then the bras are the dual vectors. The dual vectors, we denote them this way. They are row vectors, right? There's a one-to-one correspondence between the bras, the kets and bras, and that is through the operation dagger. So the operation dagger, we explained that it's a composition of 2 steps. First, you take the transpose, and then element by element, you take complex conjugation. So for instance, if you have some complex number, C, acting on the vector ket alpha, the dagger of that, complex conjugate of that, complex transpose or Hermitian transpose, I forget what they call it, dagger of it, is ket alpha C star. Star is just, C is just a complex number, and this is a complex conjugate of it, right? Any questions about this? So this is just an example of a 2-dimensional complex vector space. We call this a qubit, quantum bit, because bits are two possibilities, 0s and 1s. Here we can have a general ket as in a superposition of them, which means that it's a 2-dimensional vector as opposed to a binary thing. All right, we define inner products between bras and kets. So this is just for the level of this course, it's just simply the matrix multiplication of a row vector with a column vector that gives a complex number, right? And you could easily convince yourself that bracket of alpha and beta dagger is just a complex conjugate of it, because this is just a complex number, and is equal to bra beta ket alpha. Then we said that, so this is, in the case of, you're probably familiar with real vector spaces. And in that case, it's a similar story, but in that case, we define the length of a vector as the square root of the bracket of the vector. Now here, the notion of a length for complex vectors is, we call it a norm, and it's just square root of bracket alpha with itself. So the norm of a vector is this, and it's non-negative. And this, when we said that dagger has comprised of 2 steps, of transpose and complex conjugation, that complex conjugation we said is essential for the bracket for the norm of a vector, complex vector, to come out as non-negative, if this to have the interpretation of norm. When it's 0, we called it a null vector, which is just a vector of zeros, a bunch of zeros, right? We talked about linear operators in this course, and basically in quantum mechanics, we only talk about linear operators. Linear operators means that they act on kets and just numbers come out and they just multiply. Matrix multiplication is precisely the manifestation of the fact that these are linear operators. So if you recall from your linear algebra courses. So when an operator A acts on a ket alpha, an operator, we model it by a D by D matrix that acts on the right on a ket, or it could act on the left on a bra, right? So you could multiply a row vector by a matrix from the D by D matrix, or a square matrix from the left, or you could multiply a column vector on the right. Now, if you do both, if you take the multiply by bra on the left and a ket on the right, this is simply a matrix element. This is like it's a complex number, right? And as we said before, it's a complex number, if you take the complex conjugate of it, it's just basically element by element, you reverse them. So beta comes here, A dagger becomes A, and alpha comes here, right? It's just should be a familiar thing in matrix for matrices as well. So if you have A, B dagger, this is B dagger, A dagger, right? So dagger operation reverses order. The same is true for transpose for real matrices, right? All right, any questions? We define Hermitian operators. Hermitian operators or self-adjoint operators. These are operators A that are equal to their dagger. We sometimes define an anti-Hermitian operator as an operator which is equal to minus its dagger. That's just for you guys to know. Do I want to comment on this? I won't. Orthogonal eigenvectors. We talked about orthogonal eigenvectors, and that's a set of eigenvectors of an operator could be. Oh, sorry. Actually, did we talk about this? Maybe we ran out of time. But okay, so let me just define this. If we have two eigenvectors, they are orthogonal. A and A prime are orthogonal if their bracket is just delta of A prime, norm of A. Right? We say, so if you have a whole bunch of orthogonal vectors that provide a basis for the space, for example, the two-dimensional qubit Hilbert space, is a basis for it is ket plus ket minus, right? 1, 0, 0, 1. Then if you make sure that every single eigenvector is normalized to 1, right, has norm unit norm, then you call these guys, you call such a basis an orthonormal. So if it's called orthogonal basis, if they're pairwise orthogonal, and if they're pairwise orthogonal, and on top of it, every vector element has unit norm, then we call it orthonormal. Of course, when we have kets and bras, by constructing a bracket, we get a complex number by matrix multiplication, but you could also do matrix multiplication in the reverse way. This is an outer product where you do a ket bra, right? And the result is a D by D matrix, right? Now, if you take, and this I don't think I mentioned, but now I'm just gonna say it now, and we're gonna come back to it. Now, immediately I can make this comment. If you take a ket and construct the outer product of it with itself, so ket alpha bra alpha, that guy is a projection, is an example of a projection operator. What is the definition of a projection operator? An operator is called a projection if it's Hermitian and it squares to itself. So you could check that explicitly, that this is Hermitian, right? Because if you take the dagger of it, it becomes again ket alpha bra alpha. And you could also check explicitly that it squares to itself, right? That's easy to check. Alpha alpha multiplied by alpha alpha is just alpha alpha. Why? Because the ket alpha has unit norm, right? Is that clear? So this was a quick summary of lecture 2.
I have a question.
Yes.
What is it's just about the writing. You have the orthonormal eigenvectors with the in blue there. You have
yes.
a delta, and then what is the subscript on that?
Sorry, here. Delta
yeah.
AA prime. AA prime.
AA prime?
Yeah, AA prime.
Okay. Okay, thank you.
Yeah. Sorry, if my handwriting is hard to read, please ask questions. So it's just that if you have two vectors, we said we use this notation that we use these labels. Yeah, good. All right. Okay, so we're gonna start lecture 3, but before I start, let me ask another time. Are there any other questions? All right, good. Let me just 1 second. I'm gonna turn on the. Okay, so we said in the past that we're gonna use kets as examples of states. Then we said that our observables are going to be operators. Now, here is the very first important principle. Our observables are not any operator. The observables are self-adjoint operators. So observables are self-adjoint. Why is that? Well, we're going to build towards that, but let's say for now, that's like a principle of quantum mechanics. But now let me prove a theorem about what is special about self-adjoint Hermitian operators, right? Hermitian or self-adjoint, I use them interchangeably. They're the same thing in finite dimensional Hilbert spaces. So if we have a Hermitian operator, there's some nice facts about it. First, the eigenvalues of Hermitian operators are real. Second, the eigenvectors of different eigenvalues are orthonormal. So these are two things you need to know. If you have a Hermitian operator, its eigenvalues are always real, and its eigenvectors of different eigenvalues are orthonormal. They're orthogonal. All right, so let's prove that. So recall that so imagine A is a self-adjoint operator, A equal A dagger, right? A acting on, I'm gonna denote by A prime, ket A prime, the vector with the eigenvalue A prime. That was the notation we used, right? So what am I gonna do? I'm gonna do the following. I'm gonna calculate A minus A prime A alpha equal to 0. So far it's obvious, right? But then first I act with A on the left on A double prime. First I act on the right. Oops, sorry, my apologies for my notation. It's A prime, A prime. First I act here on A prime. I get this term, A prime, A double prime, A prime. Then the next one, I act on the left. So I end up with this expression. I get A prime minus A double prime star complex conjugate is A double prime A prime. The reason for that is that when you act on the left, you get the eigenvalue, but it's complex conjugate, right? So now this equation has to hold always, right? So imagine first the setup where the eigenvalues are not equal. So A prime is not equal to A double prime star. Then their corresponding eigenvectors must be orthogonal, right? Because this equation has to be 0. If this is non-zero, this is 0, which means that the corresponding eigenvectors are orthogonal. Now, if this is not 0, for example, A double prime is equal to A prime, in which case this is just the norm of the eigenvector and it's not 0, then you should have the left term equal to 0, which means that A prime has to be minus A prime star. Has to be equal to A prime star, which means that A prime is real, right? So in summary, what we learn is that eigenvalues of Hermitian operators must be real. That's statement number 1. Statement number 2, the eigenvectors that correspond to different eigenvalues are orthogonal for Hermitian operators. In this story, it was essential that they are Hermitian operators. Is that clear? Are there any questions about this? Good. All right. Maybe I should pause. I think this is an important result. Are there any questions? So we, in one line, approved both statements, right? Now I've used an assumption here that I didn't clarify. Can anyone point out what is the assumption that I've assumed, but I've used? I'm hiding behind the notation. Any thoughts? The assumption I use is that the operator is non-degenerate, meaning that you can use this notation. It never happens that two inequivalent eigenvectors have the same eigenvalue. If that happens, this proof has to be done more carefully. We're going to come back to this at the end of this lecture. Good? Any questions? So based on what we said, yes.
I have a question.
Yeah.
What is the word you used to describe the operator where A equals a dagger?
Hermitian, or you could call it self-adjoint. They mean the same thing. Often physicists say Hermitian, often mathematicians say self-adjoint. That's just terminology. Any other questions? So from this, you already learned that eigenvalues of observables in quantum mechanics are always real, right? So even though we are dealing with a formalism which uses complex vector spaces, what we use as observables will always have eigenvalues that are real. Good? All right. So it's based on what I just told you. Every observable, every Hermitian operator its eigenvectors will form a basis. It's an orthogonal basis, right? And if it's convenient to make these guys unit norm, right? So then we can always represent observables using their eigenbasis, which is orthonormal, right? Orthogonal, pairwise perpendicular, and unit norm for every eigenvector. All right. Now, these guys.
One second.
Yes.
Do you mind scrolling up just the proof for 1 second?
Yes.
That last line is, why isn't it if A double prime star equals A prime?
Oh no. So sorry. You see, I'm using A prime and A double prime as eigenvalues that are defined.
Oh, I see. Okay.
With respect to the ket.
Yeah. Got it. Sorry. Okay. Yeah.
Okay. Yeah. Sure. Yeah. The notation is ultra compact, but I assure you that it really, really helps. It gets some. It takes some getting used to, but it's very convenient notation. Of course, if you have degeneracies, it gets really messy. All right. So now another thing that I haven't described to you, but it's easy for you guys to prove. I might probably include it in the homework, or if you have from your linear algebra, you already probably know this statement. I've been calling the set of eigenvectors of the Hermitian operator as a basis. That means that they span the Hilbert space. This means that every vector, an arbitrary ket, could be expanded in terms of the orthonormal basis eigenoperators of your favorite observable. The matrix coefficients are precisely these brackets. So the way to think about it, this you could convince yourself of using matrix multiplication. If you have an arbitrary matrix, like just let me give you an example. For example, consider your arbitrary matrix be C1 and C2. And this is C1, 1, 0 plus C2, 0, 1. And these are the eigenkets. They form the eigenbasis of which operator? Sigma of Z. This observable. They could check they're self-adjoint. So these guys are matrix elements. This is to be understood as the very familiar statement in linear algebra. If these are a basis, an orthonormal basis, you could take a vector and expand it in terms of a basis, and these guys, the inner product, these guys are going to be the coefficients, right? These guys, one by one, they're going to be the coefficients. So keep this notation in mind because it's a super convenient notation. Any questions? So what did we say in summary? Oh, sorry. Well, let me pause for questions. Any questions?
Question. A operator, is it formed from the alpha kets?
So A is any operator. It's a D by D matrix, right? A is any operator that is D by D matrix. I use that operator to define a basis. Now that I've defined the basis, I can expand an arbitrary vector in that basis. I'll actually, this might sound very formal, but I'm going to explain that in a second. The reason we do this is because we want to explain the idea of a measurement. So let me clarify. Imagine what you're doing is the following. Just recall that we had, so you have a state, say alpha, that comes in, you perform a measurement sigma z, right? This guy that comes in, we're going to describe the measurement. There were two outcomes, right? There were two possible outcomes, +1 and -1. We're going to describe this. This description, what comes out, the way that the measurement will be performed will depend on what measurement you're doing. So this ket, to understand how the measurement acts, you have to take the ket and expand it in the eigenbasis of your observable sigma z. If I replace my observable by sigma x and measure the same state, now what happens is that now I have to take this guy at the orthonormal basis of sigma x and expand this, right? So these two are inequivalent things. They're not the same thing. Good. I'm going to explain that in a second. Any other questions? All right, so let's describe measurement. This is where we're going to say, again, I'm going to say, describe the way it's, the way we describe measurements in quantum mechanics. I absolutely encourage you guys to just sit back and spend in your spare time some time just purely thinking about this. This is where all the magic is. All the completely crazy counterintuitive behavior of quantum mechanics that has to do with the absence of a classical reality or predetermined values has to do with, is it taken into account in this step? Well, there are several steps, but this is one aspect of it. So let me describe it. Imagine you have a Hermitian operator. A is equal to A dagger. That's Hermitian operator. So it's an observable. For example, sigma x, sigma y, or sigma z. Sorry, I calling them sigma. I think in the last lectures I've been calling them sz, sy, sx. I apologize. I think I've been using a different convention. You remember this, right? This is measurements that of the spin in the x direction in Stern-Gerlach, in the y direction, and the z direction. So if you want to know what happens in a measurement of an observable A, you first take your vector, which describes your state, your ket, your column vector, and expand it in the eigenbasis of the corresponding observable you're observing. Okay, so that step is good. Then the measurement happens. I'm going to describe what happens during the measurement. But after the measurement happens, the state just arbitrarily goes to, well, I'll describe, to one of the eigenkets. So before it comes in as a superposition of the eigenkets of the measurement, what comes out is an eigenket, always. So a message, you could say that the system, the measurement throws the system into some eigenket, eigenvector. Or you could say the measurement changes the state. Do you know why it's the eigenket? Anyone can guess based on the Stern-Gerlach that we've seen so far? Why is it the eigenket? That is required by just the things that we've said. So alpha comes in, +1 -1. Oops. Let's say we consider +1 here, right? Now, in our description, the state should be thrown in ket 0, right? The reason is that if you measure SZ again, it should always consistently give you +1. If this were not an eigenket corresponding to +1, measuring the same observable again could reproduce a different answer. This is not what we see in Stern-Gerlach. I repeat, this is not what we see in Stern-Gerlach. Therefore, the measurement has to throw you into an eigenket.
Isn't implicit in that assumption like the time evolution doesn't like go between eigenkets?
Yeah, I'm assuming there's no time evolution happens in between. I'm assuming that you
Okay.
instantaneously do the measurements, right? This is an idealization, but as usual, if you want to just abstractly understand what is going on, we're doing that idealization for now. Let's just say very quickly perform measurements. Good. All right. So now let's describe this a little bit more. Before doing that, I want to point out a structure. Recall that our eigen up in our we said that we said that the eigenkets of self-adjoint Hermitian operator and observable provide an orthonormal basis. So if I construct this object, ket bra A, sum over A, this is the identity operator. In linear algebra, this identity has a name. This is called the resolution of identity. Or sometimes it's called the completeness relation. Right? And you could use this as an identity. You could just squeeze it in the middle of all sorts of things, right? So if you get ket alpha alpha, you could squeeze it in the middle. You get sum over A, CA squared equal to 1. Right? What is ket A bra A? I said this before. It's a projection. So when it acts on some ket alpha, it gives us the component. Right? And it also satisfies these two relations that I said before. Good. So now, actually, let me jump. Oops. Sorry. I'm missing. One second. I think I moved a slide accidentally. I moved one of my slides by accident. Yeah, I was surprised that I couldn't see the slide. All right. So let me repeat. I apologize about that. Here we go. So we were here, right? So we said that the measurement throws you into an eigenvalue. So how do we describe the measurement? If you measure an observable A that's initially before your measurement in some state ket alpha, what happens is there are D possibilities for D possible outcomes. 1 to D in D-dimensional Hilbert space. For example, if you have a cube bit, there are just 2 possible outcomes, right? In the case of spin, it was +1, -1. This has to do with the fact that it's quantized. The value that we read off, the value of the observable that we read off in the measurement is the eigenvalue. So this A1 is when the result of the measurement is A1, right? For example, we said you measure SZ and what comes out is H bar over 2. Or it comes out as minus H bar over 2, right? So this is the result that we read in the measurement. And after you read this, the state is thrown, post-measurement is thrown to the ket, is corresponding eigenket. Okay? And now this event happens with the probability, which is the bracket of this. So let me write it a little bit better. So alpha is sum. Once you expand it in this basis, this is C alpha. And this is just C alpha squared. So the component of the vector in the direction, the initial vector in the direction of the post-measurement outcome, norm of it is the probability of obtaining that result in the measurement. So you basically, quantum mechanics, the measurement process in quantum mechanics is described probabilistically. There is no way to do better. There are no predetermined values. There are no laws of nature that before the measurement can tell you deterministically what will come out. It will come out as this result with this probability, and post-measurement state is this, the state is thrown into this ket, or it comes out as this result with this probability and the ket is thrown in this, and so on and so forth. So now you should have a question. If these are probabilities, they better add up to 1. That is guaranteed by that resolution of identity that I was talking about, and the fact that these guys form or the completeness relation. We'll get to that in one slide. But let me just pause here for now and ask, is the measurement description clear? The measurement description is entirely and intrinsically probabilistic. It's inherently probabilistic. But in classical physics, when we talk about probabilities, it's because of our lack of knowledge, because our measurements are crappy, or because somehow our devices have finite resolution. Here, we're not talking about that. These probabilities are there and they're intrinsic to nature. There will never ever be a measurement that can do better than this. This is just there's a finite resolution to reality, if you wish. So these probabilities are the predictions of quantum mechanics, and you could check that these predictions are correct. So every time, so what comes in is a ket, is a state. What comes out of the measurement is a probability distribution over all sorts of different possibilities. Every time you have a probability distribution over different possibilities, you could talk about the expected value, the expectation value of that observable. So the observable alpha, A, in ket alpha, will have the expectation value, which is this, is sum over A. A is the eigenvalue. Recall that eigenvalue, as I said, is the measured value, and the probability of that measured value, which is this guy here. So this is the expected value of the measurement or the expectation value. We sometimes write it this way, sometimes write it this way. I'll try to write it this way so that's clear. It's a bracket. Any questions?
I'm wondering, does the P in the expectation value line represent probability?
Yes, yes.
Okay.
So this is a, thanks so much. I said it in Word, but I did not write it. Probability of result A, or observing measurement, observed value A. Yes. So here I wrote probabilities, right? These are C alpha squared, CA squared is the probability, sorry. I don't know why I'm using A and alpha when my handwriting is so bad, but. All right, any other questions?
Yeah, so I've got one. So in general, this expectation value will not be like one of the sort of discrete values, like in the Stern-Gerlach experiment, h bar over 2 or negative h bar over 2. It would be like 0 in that case.
Sorry,
That makes
repeat it again. So in general, it would not necessarily be discrete. If you have a continuous observable, it could be continuous, as we saw in the double slit experiment. But you said something else. What did you say?
So like in the case of like the Stern-Gerlach experiment, right? So I think the spin values were positive h bar over 2 and then negative h bar over 2. So in that case, this would work out to be 0, just as an example, I guess.
What works
the
out to be
expectation
0?
value.
The expected value?
Oh, yeah.
If the state is such that initially, so if the initial state is such that this +1 is probability half and -1 is probability half, yes, that comes out as 0.
Okay.
But that will depend on the initial state, right?
Okay. Yep.
If the initial state is anything that looks like this, you could calculate it, and it comes out as half-half, right? Because what are the C0 and C1? C0 is 1 over square root 2. If you take the norm of it, it's half. What is C1? It's 1 over square root 2, some phase. The norm of that is also half. So this state, if you measure its expectation value of SZ, in this state, you're going to get 0, indeed. But it will depend on the state.
Okay, that makes sense.
Any other questions?
I have a question. So, if you make the same measurement twice with the same observable, we should be getting the same expectation value, right? Assuming there's no time evolution.
No, you should not get the same expectation value.
I see. So if we do, but if the state
You're getting to something deep. These questions you're asking. Well, I shouldn't. If the world were classical, you would get the same expectation value. But based on the laws I described to you, you do not get the same expected value.
Okay,
so it's counterintuitive. Yeah.
So after the first measurement, say the state, the state that we're measuring, it decomposes into one of the eigenvectors, right? And then we perform the same measurement. So shouldn't we get the same? I mean, because the state is an eigen.
Yeah, it is a little bit tricky. Sorry, let me just write. So here, let me make this a little bit bigger so that you could see. Oops. No, let me just write here. I'm gonna write with red. So this is your initial state. Let's say your initial state was this square root 1, 1, right? Then what comes out of the first measurement is probability half for up and probability half for down, right? The expected value at this point is 0, right? Now, next, you have to decide what is the state that you feed in the next SZ. Right? You no longer have this state.
Yeah.
Right? So what you feed in is either +1, in which case the expected value, expectation value is going to be +1, or you feed it -1, in which case the expectation value is going to be -1.
Okay.
But you're getting to something important. You're getting into the desire to describe measurements such that the expectation value of the same measurement repeated reproduces the same answer will tell you that not all states should be represented as vectors. And we are going to introduce the density operator. These questions you're asking are perfect. So for now, the description I'm having is using these ket vectors. So here, the input has to be a vector.
Okay.
But I don't have choices. I have probability half up with probability half up, probability half down. That's not a vector, right?
Okay. Yeah.
I have to feed it either up or feed it either down, in which case the expectation value is different. These are very good questions. You're getting when I said that not all states are described using kets, this is exactly why.
Okay.
All right, any other questions?
Thank you.
Do you mind talking a little bit about what constitutes measurement physically?
Okay. Let me not do that. We're gonna discuss that in detail later. But as I said this in the beginning of the course. There are lots and lots of discussions. Like you could spend so many lectures on measurement. But my goal is to first do a first round of self-contained mathematical formalism and teach you guys how to do calculations. Then you're going to go back and redo and ask physics questions and refine it and refine it and refine it. For now, we're in the phase that I'm just teaching you how to calculate. Particularly about measurement, it's a deep philosophical and physically rich concept. So for now, accept what it is, and I'm more than happy to tell you offline or maybe in a couple of lectures from now. Okay? This is a very good idea. Remind me, I'll try to include a physics description of measurement process a couple of lectures later. But for now, I just want to get through the mathematical formulation so that you guys can get your hands dirty and calculate. Remember, I told you this law of this unsaid rule of quantum mechanics. You first learn the algebra, how things are calculated, and then gradually ask physics questions. All right. Any other questions? I don't know why I'm messed up this. All right, good. So if this is correct, it must be that if I just take these PAs, just drop this term. If I just take these PAs and sum over A's, I should get 1. That's just conservation of probabilities. Right? So let's test that. Let me just add a line here and just do the calculation for you. So if this is P of A, it should be the sum of A, P of A is 1. Probabilities should add up to 1. Right? So let's calculate that. Sum of A. I'm going to write down this norm thing as alpha A alpha. Right? Now you recognize the resolution of identity. This. That is like alpha identity operator alpha, which is like alpha alpha, which is 1. So we're good. This resolution of identity is very important. And it's a consequence of the theorem we proved that observables have eigenvectors that form an orthonormal basis. This already tells you that if you want everything to go through nicely, you should always normalize your kets to have unit norm. You should always use orthonormal bases. Otherwise, these laws need to be corrected by a bunch of coefficients. Good? I've done this here. I don't know why I repeated it up here. But yeah. Let me Yeah. Good. So now, let's think a little bit about what this is. I call this a resolution of identity. What it means is that you take the identity operator, let's say for 2x2 identity operator, and write it as this. By the way, this notation, every time I write things like this, everything I don't write, it means zero. It's zero. It means 0, 0, 0, 0, 0, 0, right? This is 0, 0. This is 1, 1, right? These are projection operators. Exactly what you expect from the notion of a projection. It takes a vector and reads off a component in a certain direction. It projects to a component in certain directions, right? They have the property that they square to themselves and they're self-adjoint of each other. I was actually planning on saying a little bit more about projection operators, but let's, in the interest of time, let me just move on. All right, let me give a bunch of examples of this. I just did, right? For example, here is the projection operator, which is ket1 bra1, which is this. Another projection operator is this, for example, the ket c1 c2 c1 star c2 star, and this is a projection operator written in a different basis, right? It's a projection operator in a different basis, not the basis of the measurement I'm describing. Now, I said this before, but let me do it again. Consider as the input of the experiment of measuring, I apologize, I say sigma z, I said SZ before. Sometimes people use the notation sigma. Your initial state is the ket C1, C2. C1, C2 are complex numbers. You measure SZ. The eigenbases of SZ are these two kets, 0 and 1. You get ket 0, which corresponds to the measured value of h bar over 2 with probability of C1 squared, or you get minus h bar over 2, that's a value, and this is the corresponding eigenket with the probability of C2 squared, and they add up to 1. That's because this ket is normalized properly. It has unit norm. So it's just conservation of probabilities, and we use resolution of identity to show that. Good. So this is our first pass at measurement process, describing a formalism for measurement process. We're gonna come back to this. This course, we're not gonna leave this alone. We're gonna be discussing this a lot. Good. All right. Okay. Let's talk a little bit more about general operators. If I have a general operator, now what I'm gonna do is I'm gonna expand it in the eigenbasis of a particular observable. For example, if this and so I can take the eigenbasis of ket A's, which in d-dimensional Hilbert space for convenience I can take to be da da da, right? So this is 0, for example, or 1 is 0 1 dot 0 da da da, or I can have 2, which is 0 0 1 da da da. You get it, right? So if I take a matrix and put two resolutions of identity from the left and from the right, what I obtain is just an expansion of the matrix in terms of its matrix elements. This is a matrix element, and I'm just summing them one by one. Let me pause here and see if this idea is clear. So the matrix elements corresponds to taking the bracket between A prime and A in some basis that is orthonormal. It'll take some getting used to and doing some calculations. But are there questions? Are there any? Is there?
I have a question.
Yes.
Where it says matrix elements underneath consider an operator, and
Yes.
it goes A prime vertical line. The thing after that, is that an X or is that two of those like little carrots?
Sorry, you're talking about this guy?
Yeah, is that X or is that
It's
two
the
different
it's the
symbols?
operator. It's the operator X.
That okay, so that's the operator.
Yeah, let me call it A because I was calling it or the letters that I use for operators are often either O. Sometimes I call them A. Sometimes I call them X. Yeah. So
It just
here,
looked
if
like
I'm calling
the
that,
beginning and end of the ket in the bras. It looked.
I know.
Couldn't tell where it started and ended.
Right. I know. Like right.
Okay, thank you.
So sometimes people precisely for that reason they write ket bras this way with a little bit of distance in between them. But I like to write them this way.
No.
Sorry. It's just faster to write this way. But anyway.
Thank you.
Yeah, I repeat, this is a super compact notation. But yeah. Thanks for
So
asking.
that,
yeah.
Sorry, that carries through into the bottom matrix that you drew.
Yeah.
The X in the middle is the operator.
Yes, sorry, I just changed it, so these are all O's. Thank you. Hopefully my O and 0 are not. Good. All right. So recall that we said we had matrix multiplication. We could multiply our matrices. And if we had observables, this multiplication has the interpretation of measuring the observables one by one after another. Which one is the one that is being measured first? The right one, the right side. And the left one, the one, so they're the order this way. Now consider an observable. So this is Z equal XY. This is an observable, this is an observable, this is a composite observable that has two steps. Consider the matrix element of A prime, A double prime of observable Z. This basis could be the basis of some other self-adjoint, some other Hermitian operator A, right? It need not be related to this. So what I can do is, so I have X and Y. So first, let me write this as, as A prime, X, Y, A double prime. Then in the next step, you insert a resolution of identity in the middle. What is this, by the way? Can anyone see what this is? This is a particular matrix element. This is the row. This is the column. This is another matrix element. This is the row. This is the column. And you're summing over, you're multiplying the column of this with the row of label of this and summing over them. Does anyone know what this is? Let me write it in a more suggestive way. Maybe you could tell. What is this? It's matrix multiplication rule that you've learned, right? You take a row and element by element multiplied by columns, right? This is matrix multiplication. This is the row, this is the column, this is the row, this is the column, you sum over A. We could do this for multiplication over the vectors as well. I think this step is sort of obvious. It's just, I'm saying that if Y is a column matrix, it will still go through. Any questions? This resolution of identity is behind a lot of these tricks. The goal of part 1 of the course is for me to, I wanted to start with this two experiments that were producing results that were hard to explain. Then based on the analogy with polarization, we use complex vector spaces to model them. I'm building linear algebra and telling you about the rules. For now, we're going through the rules. So the goal of the step one of the quantum mechanics part is just to get used to these rules, get very, very comfortable with them. And then we're gonna put more and more physics to it. And you will see actually in 2024, some physics questions about this formalism remain unanswered. It's just a dirty algebra that describes the nature to the best of our knowledge. But of course, a lot of questions you would ask are answered. But okay, good. So similarly, alpha is a row vector. So you could think of it, bra is a row vector. So you could think of a bra as like element by element expanding some eigenbasis, right? These are matrix elements. This is a row vector. And if you have a ket bra, the outer product, you could just play this game of matrix multiplication and obtain the expansion of it in a particular basis. Now, here is what I want to emphasize. Consider an observable A. We're going to expand the observable A in its own eigenbasis. So I'm going to put resolution of identity of eigenbasis from the left, sum over A, ket bra A, and resolution of identity on the right. A acting on this, well, here I'm acting on the left, so I'm getting A here. Because it's real, it doesn't matter. I don't need to put A star. A star is equal to A. And then these two guys are orthonormal. So I get delta of A prime. You sum them, you get sum over A ket bra A. So this means that every observable in its own eigenbasis is a diagonal matrix. Questions? So I've walked you through a lot of linear algebra. For the remaining 15 minutes of the course, I'm going to work out examples. Spin half systems. And we're going to go through these examples and make this a little bit more clear. But are there any questions at this point, right? Let me summarize what I've said. We discussed measurements, right? Measurement was the process where you would feed, let's say you want to measure SZ, the Z component of the spin of silver atoms. The input was a two-dimensional complex vector, column vector, ket. You measure S of X. To describe that measurement, you first have to construct the eigenbasis, the orthonormal eigenbasis that corresponds to that observable. In the case of SZ, it was ket 0, 1, ket 0, ket 1. We described the process of the measurement that through it could have D different outcomes in a D-dimensional Hilbert space, and it throws you to the corresponding eigenvector. The post-measurement state is the eigenvector that corresponds to the measure value, and the probability has to do with the component of the vector, norm of it. Sorry, I said norm. I defined norm. So it's norm squared. Yeah, I've defined norm with square root, so it's norm squared. All right. Example. So I was just saying this in words. Measurement of the Z component of spin of silver atoms gives you these kets. We're going to represent them by plus and minus. This is 1, 0. This is 0, 1. the resolution of identity. I sometimes write, by the way, this notation, let me just say it right away. Sometimes I write this identity this way, identity matrix this way. The identity is 1, 1. Sometimes I just write it as equal to 1. So I will try not to write equal to 1, but sometimes I might just write it that way. If I'm sloppy, if I forget that you guys are not familiar with the formulas and all that much, I'll try to use this funky I as identity. So every time I don't, again, let me repeat, every time I don't write anything here, it just means that these are zeros. All right. So what is the observable SZ? Observable SZ has eigenvalue h bar over 2 in ket plus bra plus, and eigenvalue minus h bar over 2 in ket minus h bar minus. This is precisely what I just said. An observable as a diagonal matrix in its eigenbasis. So this takes the form of h bar over 2 minus h bar over 2. Why is that? This must be the form of the matrix if it satisfies these eigenvalue relations. You could check that explicitly, right? If I act with this matrix on 1, 0, I'm going to get h bar over 2, 1, 0. If I act with this matrix on 0, 1, I'm going to get minus h bar over 2, 0, 1. Good? So you could write it this way. Questions? Now, so far, I've only talked about observables. We also have operators that are not observables. These are operators that are non-Hermitian. They are not Hermitian. They are not equal to their adjoint. They're not equal to their dagger. So an example would be h bar plus minus, ket plus bra minus, or we're going to call that s plus as an operator. It's not an observable. Or s minus as h bar minus plus. So this is an outer product. It's an outer product of what vectors? 1, 0, and 0, 1. When you take the outer product, you get this matrix. This is the outer product of 0, 1 and 1, 0. You get this. Yeah. This is just matrix multiplication, right? So this is s plus and this is s minus. Good? So now let's see how these operators act. When s plus acts on ket 0, you get s plus. So it evolves the eigenvector that corresponded to minus h bar 2 to the eigenvector that corresponds to plus h bar over 2. Right? How does it act on the plus h bar 2 eigenvector? So let's see. So this is s plus. I just have to do a matrix multiplication by 1, 0. I get 0, 0, so this is null. Sometimes we say in physics that it kills this state. When an operator acts on a vector and gives you 0, we say it kills that state. So in notation, this s plus is like a raising operator. It raises because it brings 0 to plus. Now it kills plus because plus could not be raised anymore. It's just a 2-level system. S minus is a lowering operator. It takes plus to minus, and it kills minus because minus could not be lowered anymore. Good? Any questions? Just gonna pause for a minute. Any questions? All right. So we had this slide before, right? But let me just repeat it because it's an important slide. You're measuring an operator observable A in some initial ket alpha. These are the outcomes. The measured values are the eigenvalues. The probabilities that correspond to them have to do with components in the direction of the corresponding eigenvector norm of it, like the norm of it, and then the post-measurement states are the corresponding kets, right? And we set the expectation values. Let's work out an example. I've said this, but I want to repeat just to make sure it clicks. I'm measuring SZ. My initial state is alpha plus alpha minus. I'm just using a different notation so that there are no mysteries, right? You get eigenvalue h bar over 2 with probability alpha plus squared, and the post-measurement state is the ket plus. You get minus h bar 2 with probability alpha minus squared, and the post-measurement is alpha. The expectation value of SC is h bar over 2 alpha plus squared minus alpha minus squared. Actually, good. So now imagine your post-measurement state is plus. Next, what we're gonna do is we're gonna do this. We measured S of Z. This was our initial state alpha. If it's plus, we're gonna measure S of X. So what should I do? Well, I can already immediately calculate the expected values. The expected value of S of X in the plus ket is 1 over square root 2. The expected value of S of X in minus is 1 over square root. My bad. Sorry. No, that's good. No. This is half. This is half. Sorry. Half. Because when we fed, why am I writing these things? Because we saw that when we feed plus 1 to measurement of S of X, half of the time it comes up as plus 1, half of the time it comes at minus 1. Actually, you know what? I think I want to run this. I'm running out of time. I will not have time to go through all of this. So let me pause here because I think I want to do justice to this. So this argument I was going to run now is about why we need complex numbers in our vectors. But actually, let me let me skip that for now. All right, I'm gonna pause. We have only 3 minutes left because I had plenty more slides to go through, and I don't think that I want to rush them. Any questions?
I'm wondering, the last example you just did, why it ended in equaling 1/2.
Let's do this. So what is the SX observable? The SX observable has well, I haven't explained this. That's the issue. Yeah, let me not. I've not told you what the SX observable is. That's sort of why I paused here. Yeah, so far let's just focus on measuring SZ. To write these equations, I have to use Stern-Gerlach. But any questions about what we've gone over? So in summary, what we did today was we introduced observables. There were Hermitian operators. We said that their eigenbasis form a complete basis that's orthonormal. The eigenvalues are real. The eigenvalues are the measured values that we see in measurements. If you see the eigenvalue alpha, the post-measurement state is ket A. Sorry, if you see eigenvalue A, the post-measurement state is ket A, and the probability that corresponds to it is the component of the initial vector in the A direction squared, norm of it, norm of squared, right? Absolute value of squared. And then we give examples from measuring, for example, SC, different spin components. We actually only did the Z component. Then I think that's basic. Oh, we said that every Hermitian operator could be written as diagonal matrix, and its eigenbasis, its own eigenbasis. And we had this identity resolution of identity that we use over and over again as a useful tool to demonstrate how operators are modeled by matrix multiplication. Any questions from lecture 3? All right, if there are no questions, thanks so much. As I said, as I promised, we're gonna have bright space and all of that once we figure that the situation with the TA is running. And the first homework, I'll try to post it early next week. I'll announce it in class. So let's aim for posting the first. I'm gonna aim for posting the first homework next Tuesday. All right. Last questions? Anything?
Are we still doing this in person next week, or is it just going to be online?
Yeah, everything is going to be in person starting next week.
Did we figure out where that's actually going to happen next week then?
It's a location that is posted on wherever is Purdue. You log into your Purdue your schedule online. That's on my Purdue or one.purdue.edu or whatever it is. Whatever is the location that has been officially signed is going to be where we're going to have the course.
I think last week I asked and you weren't sure because it just says LAMB, like LAMB, and I don't know if that means like Lambertus Hall or like there's a Lamb College of Communication or like Lambert Fieldhouse. Okay.
It's Lambert Fieldhouse, yes. Yes.
Do you have office hours?
We will decide that next week. There will be office hours, of course. Any other questions? If not, thank you so much, guys, and have a nice day.
Thank you.
Thank you.
Thanks.